Cisco Nexus switches connect servers, storage systems, firewalls, routers, and other switches inside the data center. But there is an important question. When a packet needs to leave one network and reach another network, how does the Nexus switch know where to send it? Does it simply guess? Of course not. The Nexus switch checks its routing table, compares the available paths, selects the best route, and then forwards the packet using high-speed hardware. In this first part of the Nexus routing basics, we will build the foundation. We will explain what routing is, how layer 3 routing differs from layer 2 switching, how Nexus selects routes, and how static, default, and floating static routes work. Let's get started. Let's begin with the basic idea. Routing means moving packets from one IP network to another IP network. For example, imagine that server A is in the network 10.10.10.0/24, while server B is in the network 10.20.20.0/24. Because the servers are in the different IP networks, they cannot communicate using only layer 2 switching. They need a layer 3 device to route the traffic between them. That layer 3 device could be a router, a firewall, or a multi-layer switch such as a Cisco. When the packet arrives, the Nexus switch looks at its destination IP address. It then checks the routing table and asks, do I know how to reach this destination? If the switch finds a matching route, it forwards the packet towards the correct next hop or exit interface. You can think of the routing table as a map. It tells the Nexus switch where different networks are located and how they can be reached. Without this map, the switch would not know where to forward packets for remote networks. Before we continue, let's make the difference between layer 2 switching and layer 3 routing very clear. At layer 2, the switch forwards Ethernet frames using MAC addresses. This normally happens between devices inside the same VLAN and the same IP network. For example, if server A and server B are both connected to VLAN 100, the switch can forward traffic between them using their MAC addresses. No routing is required. But imagine that server A is in VLAN 100 and server B is in VLAN 200. These VLANs normally represent different IP networks. The traffic must now cross from one network to another. So layer 3 routing is required. At layer 3, the Nexus switch makes its forwarding decision using the destination IP address. In simple terms, layer 2 switching keeps traffic inside the same local network. Layer 3 routing connects different networks. Modern Nexus switches can perform both jobs. They can switch frames inside a VLAN and route packets between VLANs, server networks, data center fabrics, firewalls, and external networks. On a Cisco Nexus switch, an Ethernet interface can operate as either a layer 2 switch port or a layer 3 routed port. To convert the switch port into a routed interface, we use the command no switch port. This removes the layer 2 switching function from the interface. We can then assign an IP address directly to that physical port. For example, interface Ethernet 1/1, no switch port, IP address 192.168.12.1/30, no shutdown. After this configuration, Ethernet 1/1 operates as a layer 3 routed interface. It is no longer assigned to a normal access or trunk VLAN. This type of configuration is commonly used on point-to-point links between leaf and spine switches. Each physical link can have its own small IP network, such as a /30 or /31 subnet. Using routed links instead of extending VLANs across the entire fabric creates smaller broadcast domains and a more scalable, predictable data center design. Now let's look inside the routing table. The routing table contains the networks that the Nexus switch knows about and the information required to reach them. One type is connected route. A connected route is added automatically when a layer 3 interface is operational and has an IP address. For example, if the switch interface has the address 192.168.10.1/24, Nexus knows that 192.168.10.0/24 is directly connected. Another type is a local route. A local route represents the exact IP address configured on the switch interface. In this example, the local route would normally be 192.168.10.1/32. The routing table can also contain static routes. These are routes manually configured by an administrator. Finally, it can contain dynamic routes learned through routing protocols such as OSPF, EIGRP, or BGP. We can view the IPv4 routing table by entering Show IP Route. The route code at the beginning of each entry tells us where the route came from. For example, C means connected, L means local, S means static, O means OSPF, D means EIGRP, and B means BGP. Understanding these codes makes it much easier to read and troubleshoot the routing table. A Nexus switch may know several possible routes toward a destination. So, how does it decide which route to use? The first rule is longest prefix match. This means Nexus prefers the most specific route that matches the packet's destination IP address. Imagine that the routing table contains these two routes, 10.0.0.0/8 and 10.10.10.0/24. Now a packet arrives with the destination address 10.10.10.50. Both routes match that address. However, the /24 route describes a much smaller and more specific network than the /8 route. Therefore, Nexus selects the 10.10.10.0/24 route. The longer prefix always wins. This happens before Nexus considers administrative distance or routing metrics. A useful way to understand this is to think about a postal address. A country name is useful, but a city, street, and building number provides a much more precise destination. Routing works in a similar way. The most specific matching route is selected first. What happens when Nexus learns the same destination with the same prefix length from different routing sources? For example, the switch may learn 10.20.0.0/16 through OSPF and also have a static route for exactly the same network. In this case, Nexus uses administrative distance. Administrative distance is a value that represents how trustworthy a routing source is considered to be. A lower administrative distance is preferred. A directly connected route has an administrative distance of 0. A static route normally has an administrative distance of 1. Internal EIGRP normally uses 90, while OSPF normally uses 110. External EIGRP normally uses 170. BGP administrative distance depends on whether the route was learned through external or internal BGP. The important point is that administrative distance compares routes learned from different sources. If a static route and an OSPF route both describe the same prefix, the static route normally wins because one is lower than 110. However, administrative distance is considered only after longest prefix match. A more specific OSPF route can still be selected over a less specific static route. First, Nexus find the longest matching prefix. Then, if multiple routes have that same prefix length, it compares their administrative distance. Administrative distance compares different routing sources. But what happens when multiple routes are learned through the same routing protocols? In that case, the protocol metric is used. A metric is a value calculated by a routing protocol to compare different paths toward the same destination. In most cases, the lower metric is preferred. However, every routing protocol calculates its metric differently. OSPF uses cost. OSPF cost is normally based on the bandwidth of the interfaces along the path. A path with a total OSPF cost of 10 is preferred over a path with a cost of 30. EIGRP uses a composite metric. By default, bandwidth and delay are the most important values in the EIGRP calculation. EIGRP can also consider reliability and load, although these are not normally enabled in the default metric calculation. BGP works differently. It uses path attributes and routing policy rather than one simple technical metric. Attributes such as local preference, AS path, origin, MED, and other values can influence the selected route. So the route selection order is important. First, Nexus checks the longest prefix match. If the prefix length is the same but the routes come from different sources, it compares administrative distance. If the routes come from the same routing protocol, the protocol's metric or path selection process decides the best path. Static routing is the simplest way to add a remote network to the routing table. A static route is configured manually by the network administrator. For example, IP route 10.30.30.0/24, 10.20.20.1. This command tells the Nexus switch to reach the network 10.30.30.0/24. Send the packet to the next hop address 10.20.20.1. The first part identifies the destination network. The second part identifies the next hop router. Static routes are easy to understand and very predictable. The route remains configured until an administrator changes or removes it. Static routing also generates no routing protocol updates and requires very little control plane processing. It can be useful for small networks, management networks, stop networks, special service routes, or environments where only one path exists. However, static routes do not automatically discover new networks. They also do not automatically calculate a new path when the topology changes. If the network contains hundreds of destinations and many Nexus switches, configuring and maintaining every route manually becomes difficult. That is why static routing works best when the topology is small, stable, and easy to manage. A default route is a special type of route used when no more specific route matches the destination. For IPv4, the default route is written as 0.0.0.0/0. Because the prefix length is 0, it is the least specific route possible. That means it can match every IPv4 destination, but it is selected only when the routing table does not contain a more specific match. For example, IP route 0.0.0.0/0 192.168.1.1. These commands tell the Nexus switch if you do not have a more specific route for the destination, send the packet to 192.168.1.1. The default route is also known as the route of last resort. In the data center, it may point toward an upstream router, border leaf, firewall, WAN edge, or internal gateway. For example, an internal server may send traffic towards a public destination such as 8.8.8.8. The Nexus switch checks its routing table. If it does not have a specific route for that destination, it uses the default route and forwards the packet to the upstream gateway. The default route simplifies the routing table because the switch does not need an individual entry for every possible external destination. However, the next hop must be configured correctly and must be reachable. Otherwise, unknown traffic may be sent in the wrong direction or dropped. Static routes can also be used as backup routes. This is known as a floating static route. A floating static route is configured with a higher administrative distance than the primary route. Because a lower administrative distance is preferred, the backup static route normally remains inactive. It appears to float above the active routing table. For example, imagine that the primary path to 172.16.0.0/16 goes through router 1. We might configure IP route 172.16.0.0/16, 192.168.1.1, 10. We can then configure a backup path through router 2, IP route 172.16.0.0/16, 192.168.2.1, 200. The route through router 1 has an administrative distance of 10. The route through router 2 has an administrative distance of 200. As long as the primary route remains available, Nexus prefers the path with the lower value. If the primary route is removed from the routing table, the floating static route becomes active. This provides a simple method of backup connectivity. However, basic static routing may only detect whether the local interface or next hop is available. It may not detect a failure farther along the path. For more intelligence, failover, object tracking, or another reachability mechanism may be combined with the static route. Static routing is useful, but networks do not remain unchanged forever. Links fail, new networks are added, devices are replaced, sites grow, and traffic patterns change. In a small environment, an administrator may be able to update every static route manually. In a large data center, that quickly becomes unrealistic. Dynamic routing protocols allow routers and layer 3 switches to discover, exchange, and update routing information automatically. Instead of configuring every remote network on every device, routing neighbors share reachability information. When a link fails, the routing protocol detects the change. It removes the failed path, recalculates the best available route, and updates the routing table. This process is known as convergence. Dynamic routing provides several important benefits. It reduces manual configuration. It adapts to topology changes. It can select better paths using routing metrics. It scales to much larger environments and reduces the risk of human error. In a data center, fast convergence is especially important. A signal fade link should not cause a long interruption for applications, servers, or virtual machines. Dynamic routing allows the network to react automatically instead of waiting for an administrator to make manual changes. Routing protocols are commonly divided into two major categories. The first category is Interior Gateway Protocols, or IGPs. IGPs operate inside a single autonomous system. An autonomous system is a network or group of networks managed under one common administrative policy. Examples of IGPs include OSPF, EIGRP, ISIS, and RIP. These protocols focus on finding efficient internal paths and converging quickly when the topology changes. For example, OSPF may be used between Nexus, leaf, and spine switches inside one data center. The second category is Exterior Gateway Protocols. The main exterior routing protocol used today is BGP, the Border Gateway Protocol. BGP exchanges routes between different autonomous systems. For example, one company may use BGP to exchange routes with an internet service provider. BGP is designed for very large routing environments and provides detailed policy control. The difference is mainly about scope. An IGP helps devices find the best path inside an autonomous system. BGP connects autonomous systems and controls how routes are exchanged between them. These protocol types often work together. An IGP can carry internal routing information towards a border router. The border router then uses BGP to advertise selected network externally and lane routes from other autonomous systems. Interior routing protocols can also be grouped by how they learn and understand the network. One category is distance vector routing. A distance vector router tells its neighbors which networks it can reach and how far away those networks are. In a simple example, a router may tell a neighbor, "I can reach this network in 3 hops." The router normally depends on its neighbors to pass routing information through the network. Traditional distance vector protocols do not build a complete map of the entire topology. RIP is a classic distance vector protocol. EIGRP is normally described as an advanced distance vector protocol because it uses more sophisticated calculations and loop prevention mechanisms. The other major category is link state routing. A link state router advertises information about its own links and connections. These advertisements are shared throughout the routing area. Each router then builds its own topology database, which acts like a map of the network. The router runs a shortest path algorithm against that map to calculate the best routes. OSPF and ISIS are link state protocols. Link state protocols normally converge faster and scale better in large, complex networks. However, they may also require more memory, processing, and careful design. In simple terms, distance vector protocols tell their neighbors how far away destinations are. Link state protocols describe how the network is connected. Both approaches have the same goal: to learn reachable networks, calculate the best paths, and install those paths in the routing table. Thank you for watching this